about the notation of the voltaic cell. We learned that a voltaic cell is composed of an anode and cathode. The notation, if we don't have the picture, which we normally don't, how to be able to write the notation and find out what reactions and what metals, what electrodes we are using, what electrolytes we are using. So the rule is to write the anode reaction on the left and cathode reaction on the right. Between the faces we put a bar, a single vertical bar, and for the salt bridge we have a double bar. So for such a reaction we will write what happens in the, let's say, let me erase it because I don't want it to confuse. Let's say, for example, for a cell in anode we have copper to copper. It's oxidation, right? Happens in anode. And in cathode we have zinc 2 to zinc. So we're supposed to write the cell notation. Anode comes first on the left side and then the cathode. So we start with the metal or electrode. There is a small, not the barrier, but it shows the phase change, right? A phase change. It's a metal, but copper ions are in the solution. So you show it with a single vertical bar. That's for one electron. Then cathode is on the other side, but what is between them? What is making connection? The salt bridge. Okay, so this is the salt bridge. Double vertical bar. Then on the other side we have zinc in the solution. Right? This is what you exactly see. The metal, solution. Salt bridge, solution, metal. That's the rule. That's how you, oops, you don't have it. That's how you write the notation. So between the electrode and its solution, single vertical bar, and for the salt bridge, double vertical bar. Between the two electrodes and their electrolytes, between the two solutions, we said salt bridge separates the solutions. We have the double bar. Another different type of cell is when you are dealing with a gas. When you have gas involved in the reaction, then you need to use an inert material, a material that does not react easily, such as platinum. So, for example, if the half reaction of chlorine to chloride being reduced, chlorine is gas, right? So you have chlorine gas, right? Chloride is in the solution, it's aqueous, and you will separate the solution from your platinum, from your inert metal. If you have so this is the reduction, so platinum goes to the far right at the very end of the cell notation. That was the cathode. Now, if you have an oxidation in an anode and you have hydrogen gas to hydrogen ion in aqueous solution, then again you are dealing with gas. So because this is an anode, platinum starts again. Platinum either way it appears on the very ends of the cell notation. So for anode, because anode is written on the left side, so platinum is the first one appearing, and then you have hydrogen gas, and then you have hydrogen ion in the aqueous solution. Okay, so that's the difference. In the cathode, the inert metal is on the very far right, and the anode is in the very far left. It's the best if you want to be very detailed, to write the concentrations of the solutions and pressure of the gases. So for example, let's say a cell notation, the same way as you have it on slide number 43, is this. So you see, it shows that copper is oxidized to copper ion in the anode, and fluorine gas has been reduced to fluoride. The molarity of the copper solution is 1 molar. The partial pressure of fluorine gas is 1 atmosphere, and concentration of fluoride solution is 1 molar. Since you're dealing with a gas, you would need to have the inert platinum electrode. You ready to work backwards? We give you the cell notation, you write the reaction. All right? You have an example on slide number 44. A cell notation is given: aluminum solid, aluminum ion. This is salt bridge, right? This means that on the other side you have the reduction. Alright, so this side is anode or oxidation. This side you have cathode or reduction. So you have aluminum 3, and 3 electrons are released. That's the oxidation half reaction. Excuse me. And what do you have on the reduction, on the cathode? You have copper 2. How many electrons does copper need? 2 electrons. Now, you cannot add them to each other and get the final because your electrons are not the same. So what do? You multiply this by 2 and multiply this by 3. So you will have 2 aluminum solid, 2 aluminum ions plus 6 electrons, and the other equation, 3 copper 2 plus 6 electrons gives 3 solid copper. Now you can add them and cancel the electrons. So 2 aluminum plus 3 copper ion gives 2 aluminum ion plus 3 copper metals. That's the final equation for that cell notation. Now we can focus more on the flow of electrons and do some more calculations on our about the electrochemical reactions. But we said we have two electrodes, and between the two electrodes we have a potential difference. Just like when you have a part of a house with lower temperature and a part of the house with higher temperature, the temperature, if you let it some time, if allow some time, the temperature, the heat goes from higher to the lower part. So potential difference is the same. Difference in electric potential or electric pressure, when one side has more pressure, one side has less pressure, between the 2 points. Potential difference is measured as volts. So what you see, potential difference is shown in volts, which is abbreviated in V. Okay, so the electric work, the work that we get from the batteries, electrical work, that we get is the charge times the potential difference. How many electrons, what's the charge, times potential difference. So the electrical work unit is J, joules, and charge is C, coulombs, and V. So you can find the potential difference in J over C. If you need to work on these, you know that the formula will be given. The magnitude of the charge on 1 mole of electron, how much charge an electron can transfer, is shown in Faraday constant. Faraday constant. Robert Faraday worked on it, which is 96,485 coulombs. Coulombs is, so that's how we get the work from our batteries. How do we know they are 12-volt battery or 4-volt battery or 16-volt batteries or 20-volt batteries? That's how it is calculated. So this is a constant which is given to you in the exam, but if you keep it somehow in mind while you are practicing on different examples, it makes it easier for you. So I'm not gonna enter into the physical aspects of voltage and the stuff because I'm not very good in physics. What we need to know at this point, which is related to our discussion, is the potential for our cells. We're talking about electrochemical cells, right? So let's talk about cell potential or electromotive force. Cell potential. The potential between the two electrodes that makes the electrons to flow. Cell potential or electromotive force. EMF. Or we just abbreviate it as E. Let me just write it here. Is E. Cell. We can determine it with the digital voltmeter, yes. When you think that your battery is done, it's about to die, perhaps you have done it, or your father or somebody in your home has measured the voltage of the battery to see if it is worth to keep it or it has to be dumped. So we use the voltmeter. and it measures the potential between the anode and cathode. You remember the last chapter, you had maximum work for a cell. This is the formula. The maximum work you can get from a battery is the number of moles of electrons. Of electrons, and F is Faraday constant, and E is the E of the cell, potential of the cell. So we can say most of the times we need to find the N, or let's say all the times we have to find N for a reaction. So 2Al plus 3Cu, it gives 2Al positive 3 aqueous plus 3Cu solid. We're supposed to, I'm working on slide number 55. The EMF of a particular cell is, E of the cell is how much given? 0.500 volts. So this is given. Calculate the maximum electrical work of the cell obtained from 1 gram of aluminum. 1 gram of aluminum. So first let's find out what is the number of electrons. If you remember, I'm not going to do it again. In the previous example, go back to slide number 46. If you go back to slide number 46, then you will have the number of electrons. How many electrons did you have? 6, right? So any 6, E cell is 0.500 volts, and this is V, by the way. And what else do we need? Faraday constant 485 coulombs. Correct? Now, let's find out W max for 6 moles of electrons. 6 times F minus, it's minus NF. 6 times 96, this is 6 moles. 96,485 coulombs per mole. And E cell is 0.500 volts. Volts is joules per coulomb, right? Because we want to be able to cancel. So W max is how much? We didn't consider the negative because negative is showing the direction. It's not a mathematical negative sign. So 2.89 times 10 to the 5th joules. This amount is for 2 moles of aluminum, right? It's for 2 moles of aluminum. But in the question, we wanted just for the gram, for 1 gram. So we know that 1 mole of aluminum is how much? How many grams? 26.98 grams. So when you it's going to be 5.36, find it in kilojoules. Kilojoules, and this is in per grams. So that's how you use this formula and the number. Another formula that, or before that, let's talk about electrode potentials. The potential of the cell we just talked talked about cell potential is the potential of oxidation and reduction, both of them. E of cell is E of oxidation plus E of reduction, if you say E is the potential. So on slide 60 and 61 you have electrode potentials. Electrode potentials. And according to this table, the more negative, or let's just more negative potentials means you have oxidation. I'll tell you why I'm saying that. And more positive is for reduction, which happens in cathode. All right, so at the end, what you need to know is that E of cell, E of cathode, minus E of anode. If you pay attention to that table again, you will see the potential for hydrogen is 0. So keep it in mind. For hydrogen is 0. Now, let's see how we can use this formula and the potential, the electrode potentials on that table. Slide 60 and 61. The question on slide 63 is talking about this cell notation. At the cathode, copper is reduced to, copper ion is reduced to copper 2, to copper solid. This side we said is supposed to be anode, right? Oxidation. And this side is cathode, reduction, correct? And it shows it, oxidation, and these two, reduction. So E for copper is positive 34 volts, and for aluminum is 1.66 volts, right? Because what you see on the table is for its reductions. So for its oxidation, it's the opposite sign. Then now E of cell is, or you just can keep it as, wait a minute, let me go and check that. For aluminum, you have minus 166. Okay, so let's keep it as minus 166 regardless of what you have. We said the more negative one is for anode, right? So put it for anode and put this one for cathode, right? It matches for copper cathode, for aluminum anode. So E of cell is 0.34 minus 1.66, which is plus. So you will have almost 2 volts. You can get 2 volts from this battery or whatever cell it is. You have in that table on page, on slide 60 and 61, you have standard electrode potentials. These are E standard. which shows if you're dealing with a solution means 1 molar solution, just like anything is standard so far we have talked about. Or if you're talking about a gas, means 1 atmosphere of the gas. So that's what the standard electropotentials are signifying. All right. So I'm sure now you can work on. I leave the example on slide 65 on you. Try not to look at the answer. It's very similar to what we worked on. It is in a different wording. It's different. It's about a fuel for the photovoltaic cell that NASA uses. So try to figure out which one is anode, which one is cathode, and find the E of the cell. Now, the next concept is to compare, how to compare oxidizing strengths. I almost told you, but let's work on it again. Comparing oxidizing strengths. So if you look at look back at the slides 60 and 61, you see we know that oxidizing agent, you remember it from Chem 1. Oxidizing agent means that the substance that forces oxidation in the other substance. So it will be reduce itself, correct? Reduce itself. So the one which is reduced, I told you, is the one with the more positive E standard, more positive potential, electric potential. At the same time, reducing agent, if you are comparing the oxidizing or reducing strengths, let's do it at the same time. It would be the reducing agent will be oxidize itself because it has to force the reduction on the other one. So it's oxidized itself. So it's the more negative one. When I teach it, I always say anode, oxidation happens in the anode, right? Anode and negative, they both have N. So negative for anode, so positive is going to be for cathode. You have an example on slide number 69 about it. The question is asking, which is a stronger reducing agent under standard conditions? SN2 to SN4 or Fe to Fe2. The standard potential for Sn, which is the standard sign is missing on the PowerPoint slides, is 0.15 volts, and for Fe is minus 41. The question is asking which one is a stronger reducing agent. Reducing agent means it should oxidize better, right? Oxidize itself. The one which is oxidized will be in anode, right? Oxidation happens in anode. So you're looking for a more negative electrode, more negative potential. Which one? This one. So Fe is a stronger reducing agent because it's oxidized better. I leave the other part on you is asking what is the stronger oxidizing agent under standard conditions? chlorine or a manganese, permanganate. So you say oxidizing agent, it should be reduce itself, and you pick the more positive one, which is permanganate. Okay. Also, you can predict the direction of the reaction based on the electrode potentials. You can predict the direction of the reaction when you compare the relative oxidizing or reducing strengths. Like the question is that, will dichromate ion oxidize manganese 2-ion to permanganate ion in acidic solution under standard conditions? So dichromate changes to chromium. That's what the question is saying. Potential, electropotential is 1.33 volts, and for permanganate to manganese 2, standard electrode potential is 1.49. So if dichromate ion should oxidize manganese, it should be reduce itself, right? Reduce and oxidize. For the one which is oxidized, then it has to be in anode, right? And it has to be more negative. But you see, here chromate is more negative. It's smaller, right? So dichromate is not able to oxidize manganese to permanganate. You can disregard slides 73 and 4 and 5. They might be a little bit confusing, and I promise you won't have any questions about them. So in the next in the next video, we will start working on slide 77 through the end of the chapter, working on the stoichiometry and more calculations about the cells with the Gibbs free energy and relate them to equilibrium constant.